Okay, I guess we can start. Welcome, good afternoon, everyone. Welcome to Engineering Physics Graduate Student Seminar. So as you can see from this slide, we're going to have an excellent speaker today to talk about a new interesting material for the LED, laser diode emission devices. So I would like to invite the speaker to introduce himself and his research group activities, and yes, we'll go from there. Simon, it's your floor now.
Thank you very much, Dr. Zhu, and thank you everyone for attending this seminar. The subject that we're going to discuss today is lateral carrier diffusion-based light-emitting diodes. And we'll start off with an introduction to myself and our team. We're going to talk about our research motivation, in which we'll cover a brief history of televisions, our desire, the challenges that we faced, and introduce silicon carbide as a carrier transport layer. We will then move into our what if statements, cover some of the challenges related to our what if statements, and obviously COVID. We will then cover our experiments and discuss our observations. We'll share with you a model for lateral carrier diffusion and end the presentation with proposed next steps. My name is Salman Bawa. I was born in Karachi, Sindh, Pakistan, a metropolitan seaport city in the south of Pakistan, about the size of Toronto and packed with 15 million people. So that's about half the size of Canada. A pretty interesting city in terms of its infrastructure. And you can see from the railway diagram here, or railway photo here, that the city had infrastructure from the colonial era still in operations. Here is where I did my undergraduate in electronics, and then went on to work for a couple of years in the telecom industry. In 2009, I moved to Canada in Hamilton and completed my engineering, entrepreneurship, and innovation. My studies led to the commercialization of two products. One is the solar-powered venting skylight by Velux, and the other is RV chandelier for the recreational vehicle and cargo tool trailer industry. This is a very specific kind of LED ring that goes around the ceiling vent of cargo tool trailers and recreational vehicles, available in both Canada and the US. At the same time, I worked for a couple startup companies, one called Axiom, which is a web-based document and video annotation software out of Waterloo, and Trita, which is a health technology platform for patients with dementia and their caregivers based out of Toronto. In 2015, I joined my alma mater, McMaster, in the School of Engineering Practice and Technology. And here is where I'm working to develop relationships with industry, municipality, not-for-profits, in the areas of automation, engineering design, manufacturing, public policy, and systems and technology. In 2009, I started doing my PhD part-time with the idea of how should we benefit the masses via technology. This is exactly where my passion is. And the research interest is trying to use abundant materials for light emission while retaining efficiency. Our team is supervised by Dr. Adrian Kitai. He's an expert in anything that consists of light absorption or light emission, such as solar powers, displays, television, projection screens. He's also involved in a number of research and technology-based startups. The latest example is Lightboard Depot, which is essentially a light board that professors can use to teach in classroom in a virtual setting, pretty much needed in the pandemic that we are all in. In fact, Dr. Kitai loves light so much, his favorite quote that his students know is "light turns me on." Our team comprises of Sam, Tingwei, Liam, myself, and Dr. Kitai, and we all contributed in the work that today I have the fortune to present to all of you. So let's start with a brief history of television. And I was researching over the internet, and the best figure that I could find is this. So over a period of a generation, we have been successful in giving the television the figure that we all desire. And as televisions are becoming more flat and flatter, the technology is moving towards micro LEDs. And if you look at micro LEDs, the TV would then be comprised of tens of millions of pixels, each pixel being an LED. And so we need to take into consideration the cost of such a TV, and also whether the materials that we want to use to make these tens of millions of LEDs, are they abundant? Now, our desire stems from the from the feeling or from the want of having more. So if you look at the image on the screen, on the left is a conventional LED versus on the right is a micro LED. So you can see that amazing brightness and contrast and color that you get in televisions if you're using and moving to micro LED technology. But then we want more. We want modular screens. We want screens that are flexible, foldable. We want screens that are in fact scrollable as well, screens that can come out and into a scroll so that we can make it portable and carry it at different places. But here are the challenges that I would like to share with you when it comes to commercially available televisions. And I'd like to draw your attention to the technology line in this table. And you can see that as the technology moves to micro LED, the price of the television more than doubles for half the resolution. Now, we do acknowledge that when it comes to micro LEDs, there are unparalleled pros, such as brightness levels, contrast ratios, the amazing volume of colors that is possible due to the tens of millions of LEDs that we are using, the wider viewing angles, reduced power consumption, increased lifespan because it's just the micro LEDs without the need for an LCD. And the shape and size could be flexible and modular. But the con is this unaffordable, huge price tag that we are seeing. And that's one of the issues that we are trying to address. So we can take our inspiration from silicon in the solar cell market. And we can see that silicon continues to dominate the market because it is abundant and it has a low cost. And this is in spite of other technologies that are available for a solar cell that are out there. We see that silicon continues to dominate the market in spite of other technologies that are higher in efficiency than silicon. Part of the reason, in addition to abundance and low cost, is the fact that silicon was first to market, and the capital investments have been already made in infrastructure. Can we use silicon for visible light emission? Well, it's a low band gap element, and having a band gap of about 1.1 electron volt, where most of the emission would then occur in the infrared region. And it is indirect band gap, which means that the electrons and the holes, for them to recombine, the efficiency for them to recombine is low because it's phonon-assisted recombination mechanism. So let us try to introduce silicon carbide, which is a wide band gap material. The band gap varies from about 2.3 to 3.2 electron volts, which means that all colors, visible colors, are possible if we are using silicon carbide. In fact, when silicon carbide was discovered by Henry Round in 1907, he mentioned about observing several light colors: yellow, green, orange, brown, blue. Now, silicon carbide, the challenge here is it has indirect band gap, which means just like silicon, the recombination mechanism would be phonon assisted, and therefore the efficiency would be lower. However, silicon carbide has been used vastly in the electronic industry. And you can see from the graph on the screen that silicon carbide has been used for high temperature, high power device operations because it can withstand the high temperature, high power requirements. So our what if statement was, what if we try to use silicon carbide as a carrier transport layer in micro LEDs? And the reason why we are thinking in this direction is because silicon carbide comprises of silicon and carbon, which is in abundance. It would be inexpensive with increased volume production, and the fact that it can have tunable colors. So I would like to draw your attention to the figure on the right-hand side of the screen. And you can see that we have a PN junction that would be indirect band gap, such as silicon carbide. And then you see the blue arrows. What we are trying to emphasize here is that somehow, if the carriers, electrons and holes, are able to transport from the junction into the orange materials on the left and right of the PN junction, they could recombine there. But if we can use silicon carbide as a carrier transport layer, that would be something that would be helpful and try to reduce costs. So our what if statement led us to consider a number of questions. The first is, what could be the active light emission region? And since we were all physicists, we took the very physics approach to answering this question. We said, let's assume that we have achieved the active light emission region. What could be the next challenge? Well, how do we transport these carriers to the active light emission region? And we again took a physics approach saying, let's assume that we are able to transport. The question would be, what mechanism would enable the control of the flow of carriers? And this became an important question to us because if we can control the flow of carriers, we have found a way of using silicon carbide as a carrier transport layer that can then transport the carriers into another active light emitting region of the LED. And obviously we had to go through a number of experiments and modeling, and we faced COVID. So the way we tried to address the COVID challenge was to figure out what areas of expertise our team has, and essentially let the individuals progress in their area of expertise, and then combine our work together, which I have the fortune to present to you today. So what we did was to use a 4H silicon carbide, and 4H is a very common polytype of silicon carbide, and this was made available by GeneSiC. We used the junction transistor that you see in the figure on the top of the screen, and we forward biased the base collector junctions and took the electroluminescence spectra at about 0.2 amperes in room temperature and ambient conditions, using a grating spectrometer with a silicon photodiode detector. On the right of the screen, what you see is we removed the packaging of the transistor. And so you can see this blue-green light that we were able to achieve at forward bias 0.2 amperes. And this electroluminescence spectra that you see on the screen is what we got. What we got is an expected narrow peak at the blue region and a broad green emission. And let us try to figure out why we're getting this. So the narrow blue peak is a very well-known peak light emission that we get from silicon carbide band-to-band recombination. The broad green spectrum is also known and attributed to defects in silicon carbide. And our hope was that if we are able to somehow increase the defects in silicon carbide, would we be able to encourage the electrons and the holes to then transport to these defect centers and recombine there rather than recombining in the blue region? So that is what we are trying to achieve. And in order to do that, we started off by saying, could we do an etch of the edge of the transistor that we are using? So this is a very well-known anodic etch process to cause nanoporous silicon carbide using 20% HF, 5% ethanol, and 75% distilled water. The base emitter were connected to form the anode connection. Platinum was used as the cathode, and the etch was done at 13 volts, 2.8 amperes for 4 minutes. And diagrammatically, what we get is this etch at the edge of the device that is marked in the figure as nanoporous silicon carbide. What you see now on the screen is optical micrograph and scanning electron micrograph showing the depth of the nanoporous region to be about 8 to 9 micrometers. So what we did was to take the dye and figure out the electroluminescence spectra unetched and then etch. So after etching, what we are hoping is that we have caused enough defects for the electrons and holes to transport and the green light to increase. Well, here's the result after the etch. It did not increase. The green light did not increase. And so we were wondering why this happened. Why is it that the electrons and holes did not transport to the defect centers created by the etch? And one of the reasons we thought was that it's probably because the edge of the device is too far from the PN junction. So we said, okay, let's try to go to the PN junction. Let's try to create the defects there. So what we did was to move 275 micrometers from the edge of the device, cut the device, and get the electroluminescence spectra, which is on the screen, the narrow blue peak and the broad green peak as expected. Then we etched at the junction, and here's what we get. The green light increased because electrons and holes preferentially transported themselves to these defect centers where then they radiatively recombined. This increase in peak is obviously relative. And then we said, let us try to validate what's going on here. So in another sample, we cut the device at 50 micrometer from the edge of the device. So this is close to the junction, but not at the junction. It's away from the junction. And so what we get is some increase in the green emission. Once again, attributed to the carriers transporting themselves to the defect centers. So what's going on? One way to figure this out is let's try to put these electroluminescence graphs side by side. So when the dye edge is only etched, there really is no change. But when the dye is cut and etched at the junction, we see the green peak relatively rise. And when the cut and etch is away from the junction, we see some rise in the green light. And what's happening, our interpretation is lateral carrier diffusion. So there are electrons and holes that are being pumped into the PN junction. These electrons and holes preferentially diffuse to these defect centers that we have created. And then they recombine radiatively at these defect centers. So that's our interpretation of what happened in our experiments and our observations. So the graph that you see on the top of the screen is a very well-known graph of showing several mechanisms of radiative recombination, band to band, donor acceptor, free electron to defect level. But we are suggesting something different. So let's try to look from this graphic here. What we are suggesting is a PN junction that when it is forward biased, gives us a blue light with a tinge of green. But then we try to create a defect at the PN junction. And I'm just going to sketch this defect that we create. So let's say we cut this. And obviously the defect will have a depth. So we create this defect by cutting, and then we etch the junction. So these dots represent the etch. And what happens is that we have holes and we have electrons. And as they move to the PN junction, what we are saying is that they would preferentially diffuse to these defect centers that we have created and radiatively recombine there, causing now a more greenish tint to the light. Another way to interpret it is through the use of a band diagram where the defect centers are created within the band gap of the conduction and the valence bands. The carriers diffuse to these defect centers where then they radiatively recombine. And so we asked ourselves, has this ever been reported in literature? And here are two pieces of literature that we found that talk about the concept of lateral carrier diffusion, but in direct bandgap materials such as gallium nitride. So if you look at the figure on the left, you see a gallium nitride PN junction produced, and then there is this quantum well structure that is being developed here. So there is some radiative recombination happening at the junction, but then the electrons and holes also diffuse to the quantum wells where they radiatively recombine. The figure on the right uses gallium arsenide and variations of it. And you can see that as the electrons and holes move to the junction, there is some radiative recombination that would happen here, but most of it would diffuse into the intrinsic gallium arsenide region where they would then radiatively recombining, hence calling the intrinsic gallium arsenide here as the active region. So what are the constraints to lateral carrier diffusion? The first is the diffusion length of the semiconductor with respect to the device dimension, particularly the direction of the device in which these carriers diffuse. So the diffusion length is important. If the device is too wide, the carriers would just annihilate into the device and would not reach the defect centers that we have created. Another is band gap. So if it's indirect band gap, it would encourage the carriers to transport as compared to direct band gap, where the carriers would have a higher probability to radiatively recombine rather than diffuse. And another challenge is how do we extract these carriers? So one mechanism is using the porous region that we created in our experiments and try to figure out, are there any further areas or defects that we could create at these porous regions to access the carriers and have them, encourage them to radiatively recombine. Another is to use nanomaterials to cause quantum confinement such that the carriers at this surface enter into the nanomaterials and then they radiatively recombine there. A third way to look at it is, can we have a direct band gap type 1 heterojunction where we can create quantum confinement and carrier control of these carriers that are diffusing from one material into another material. And so we asked ourselves, can we actually show this through a mathematical model? And what we're going to do is to use the direct band gap type 1 heterojunction and run through a mathematical model that we would share with you. So what we see here on the screen is a device where we have three materials, EG1, which is indirect, EG2, which is also indirect, and EG3, which is direct band gap material. And the band gaps are such that they are forming type 1 heterojunction. What we are hoping is that we will have electrons and holes from EG1 enter into the material of EG2. And when they enter into the material of EG2, the idea would be that they would then diffuse into and out of the screen in the direction of the width of the device. And if the length of the device is much larger than the width of the device, then the idea would be that most of these carriers would diffuse into and out of the screen and be collected into the material of EG3. And if EG3 is direct, that's where these carriers would then radiatively recombine. So let's go over our list of assumptions. What we are doing is that we are trying to create a model inside of the indirect band gap material of EG2. We are saying that they are type 1 heterojunction. And so there is a complete carrier confinement within the material of EG2. We are saying, for ease of calculations and understanding the diffusion alone, we are saying that the diffusion lengths of electrons and holes are the same, and we'll denote it by L sub C, which is the carrier diffusion length. We would also assume uniform carrier injection rate, which means that the electrons and holes coming from the contact into the EG1 material and then falling from EG1 into EG2 would be at a uniform injection rate. We are also assuming that the length of the device is much, much larger than the width of the device, and that would help us provide the model in a one dimension. And we are assuming a high radiative recombination rate at the edges of the EG2 material. And that would mean that we are assuming that they would enter into the material of EG3. So here we have the carrier injection rate, which is given by the injection current density divided by the charge times the thickness of the device, very well-known equation. Another well-known equation is the diffusion equation that we are going to use for the material of EG2. And the well-known diffusion equation, we can generalize the equation for the change in carrier concentration to be this equation that you see on the screen. And then remember that we are assuming a very high radiative recombination at x equals 0 and x equals w. So let's go back to this figure here. We are hoping that we get all the electrons and carriers here at the center of EG2, from where they would diffuse to the edges of the device, which means that they are diffusing in the direction of the width of the device, W, which is in the direction of x-axis here. So there'll be one point which is called 0, and there's one point which will be called W. And so the electrons and holes are diffusing either towards 0, x equals 0, or they're diffusing towards x equals W. But at x equals 0 and at x equals 0 W, the change in the carrier concentration goes down to 0 because we are assuming a high radiative recombination, or we are assuming that all the electrons and holes are being collected into the material of EG3, which means that at EG2, the carrier concentration, change in carrier concentration would drop down to 0. And so we input this boundary conditions into the equation to get these two equations, which when we solve for A and B, we get the change of carrier concentration equation that you see on the screen, valid for x equals, from x equals 0 to x equals W. So let's try to plot this or sketch this. And what we see is that we get what we are looking for. So at the center of the device, there are a lot of carriers. And as the carriers diffuse to x equals 0 and x equals W, we see them drop down to 0, which is what we had expected. Then we try to bring in the famous diffusion current density equation. And you can see that this equation consists of this differentiation of the change of carrier concentration. So we differentiate the change of carrier concentration to get the equation that you see on the screen, this one in particular. And we also see that the current density, the diffusion current density, is proportional to the differentiation of the change in carrier concentration. So when we try to plot that, here's what we get. And this is exactly what we had hoped for, where if the carriers are being diffused to the edges, that the diffusion current density at the edges would be maximum and would be 0 at the center of the device. Now, at x equals w, we are getting a negative value. What it basically means is that the diffusion current density is maximum at x equals w, but it's just in the opposite direction of x equals 0. Then we put the differentiation of the carrier concentration into the equation of the current density, the diffusion current density. And we substitute R equals J sub in divided by Q times T, which is the thickness of the device, to get the ratio of the diffusion current density to the input current density. And then we express it in terms of current. So this expression here is the diffusion current divided by the input current. And this is the final equation that we get, that you see on the screen. We take this equation and we plot. And once again, we get what we expect, that at the center of the device, the ratio is 0, and the ratios are maximum at the either edges of the device. Now we want to go into the boundaries itself. So at x equals to 0 and x equals w, let's try to put that into this equation of the ratio of the current density to the input current. And what we get is this equation that you see on the screen. The reason why we are using the modulus here is because we are focusing on the magnitude of the output current, or the current that is collected into the material of EG3, to the input current. Since w says x equals w is in opposite direction to x equals 0, we are just concerned about the magnitude of the ratio and not the direction right now. So that's why we have just taken a modulus. And we plot the graph that you see on the screen here. And there are two things that we learn from this graph. One is that when the width of the device is much less than the carrier diffusion length, at either side wall, the ratio of the output diffusion current to the input current is approximately half. So it's reaching about half. Another thing is that if the width of the device is the same as the diffusion length, that is, it's 1, then the ratio of the output current to the input current is about 92% on either side, on both the side walls. So 92% of the carriers are being collected at the side walls if the width of the device is the same as the carrier diffusion length. So here we want to show you a animation, and here what you see is a spatial band diagram where you see 3 different materials: the material which is blue, the material that is brown, and the material that is green. The blue is EG1, the brown is EG2, and the green is EG3. Blue and brown materials are indirect, and the green is direct. So what you're going to see is that the electrons are essentially going to drop into the material of EG2, the brown material, where it will then diffuse and drop into the material of EG3. The holes will follow the same trend, but actually bubble up. And once they are in the direct band gap, that is where they will then radiatively recombine. And remember that we need to take care that the material of EG2, the width of the device is less than the carrier diffusion lengths for diffusion to occur. So in summary, what we have shown is the generation of defects that encourage carriers to diffuse and collect at the point where we want them to collect in the device. And that's where we can extract these carriers into another material to radiatively recombine. That's what we have proposed today. And avenues to explore would be further exploring the defect engineering. So we got the porous region, we got defect-based radiative recombination. Can we figure out how we can create more defects or figure out ways in which we are able to create further defects to cause radiative recombination? Another avenue to explore is, can we use nanomaterials to cause quantum confinement-based radiative recombination? So can we pour nanomaterials into this porous region that we have created to be the side walls of the porous region, so that the carriers exit the silicon carbide and enter these nanomaterials where they could radiatively recombine? And the third is similar to the model that we discussed. Can we have a type 1 heterojunction for quantum confinement and carrier control, so that the carriers preferentially diffuse to this direct band gap semiconductor and then radiatively recombine in there? And remember that what we are trying to do here is to use abundant materials such as silicon carbide to be the carrier transport layer in a micro LED. And if we are able to use this in micro LED TVs, we open doors to unparalleled pros, which are known for micro LEDs. But at the same time, we target to make the price really affordable by virtue of using the abundant materials as a carrier transport layer. So that is our desire and motivation for our research. I would like to thank everyone in our team for their dedication and hard work. I would also like to acknowledge our funders, NSERC, MITAX, and McMaster CSEM for allowing us to have the scanning electron micrographs particularly at the time of COVID. I would like to go back to this original figure that we started our conversation with. And we looked at one part of what happened during the generation of 1990 to 2021, which is making the TV look more slimmer and aesthetic. And you can see that there is another societal impact that this figure is talking about. And if you're concerned about that societal impact, what I have to tell you is that that's a story for another what if. Thank you very much for listening to me. And I would like to open the floor to your questions, comments, your feedback, advice, and any guidance that you have, particularly with regard to us moving forward in this direction. Thank you very much.
Excellent. Thank you very much, Simon. And I like your presentation very much. So I'd like to ask the audience first, so any comments and questions? So probably I can ask the question first. So could you please go back to your slide number 33?
Yes.
Yes, I don't see the energy diagram you shown in the presentation. Okay, you have slides. Yes, okay.
Are you able to see the animation now?
Yes, yes, yes. I like this animation very much.
Thank you.
Yeah. Okay then. So then let's pause here. And for example, that if we look at the driving force for the carrier transportation, so could you please describe the driving force? It seems that you have the step 1, step 2, and the step 3 recombination. So could you please describe step by step what's the driving force for this carrier to move forward?
Yes. So if we look at the first material, the carriers would move because of a bias. So there's an external bias. And through that external bias, the carriers are now moving, and they are then entering into, or electrons are dropping into the material with a lower energy level. and the holes are bubbling up naturally to the material of a higher energy level. Once
so
they are in this
driving force is the bias, right? It's not the voltage you applied. Okay.
Correct. Right now it's the bias. Yes.
Mm-hmm.
Then
yeah.
once they are in the material of Eg2, we can clearly see that there is a higher concentration of electrons and a higher concentration of holes here as compared to another part of this material. And that's because we have a certain width here that's less than the carrier diffusion length. And so from here into the material of Eg3, or the edge here, is diffusion. So that's the diffusion that's happening. And then the electrons would drop into the material of Eg3, and holes will bubble up into the material of Eg3 here, and then they would radiatively recombine in this material here.
Okay, so let's go back to step 2 and carrier diffusion. So is there any way to accelerate or to increase the efficiency of the carrier diffusion or the transportation in this step? So do you have any idea or suggestion on this?
To increase the efficiency of diffusion? That's a great question. I'm not sure, and I'm speculating that one is what we know is that the width of the device should be less than the carrier diffusion lengths to encourage the diffusion over recombination in the brown material or in the material of Eg2.
Okay, so you basically rely on the design of the length air. Is that RD or RW?
Correct. So far that is our thought process. If there's something else that you could advise, we would definitely try to research in that direction.
Okay, then let's look at the last step. Last step, the electron hole recombination process. And I recall that you have the enhancement of the emission around the green. So can you narrow this emission band, the spectrum?
Dr. Zhu, what you're trying to say is that could we have band gaps of different materials over here?
Yes, because we're talking about this debate, right?
Yes.
So we need a specific wavelength.
Yes, absolutely. We as long as it forms a type 1 heterojunction, as long as the green material forms a type 1 heterojunction with the brown material, so Eg3 forming a type 1 with Eg2, yes. For instance, we could use materials such as cadmium sulfide or cadmium selleride to get yellowish or red colors.
Okay, then. So you change the materials to achieve a specific color. Okay, that's very good. And maybe I should ask the audience again to see if there's any questions and comments.
I have a question.
Sure.
Thanks for a good talk. So in the recombination zone there, other than a lower band gap, direct band gap semiconductor, can you go into other options for that recombination material?
Thank you, Dr. Kitai. So this is for the Eg3 other than direct band gap materials?
Yes. What other kinds of strategies could we have for recombination?
So one strategy could be the one that we worked on in achieving the porous region. So if we cause a porous region, we know that the light emission would be at the porous region, or relatively the light emission is going to increase at the porous region. So that's one lesson that we learned through the exercise. The other strategy could be to use nano materials that could be attached to the material of EG2. And that's where the carriers would diffuse into this nanomaterial and hopefully recombine there.
Okay, and do you have evidence that an indirect bandgap material could become a direct bandgap material in the nanoscale?
Yes, Dr. Kadai, there is some research that has been done in terms of even using a material like silicon carbide. We could go from bulk trying to use a process by which we can get nano silicon carbide. And as we go smaller and smaller, the band gap becomes more and more direct.
Okay.
So that has been shown in calculations, in theory. It has been shown in the literature through one experiment that has been done, where the conclusion was that it approaches direct band gap. They didn't conclude that it becomes an exact direct band gap. They said that it approaches direct band gap.
Mm-hmm.
Okay, any other questions or comments? So probably I can ask the second question then. So you mentioned that micro LED has a very high price tag. So could you please explain why?
Yes. Maybe I can just go back to the slide that had the price comparison very quickly. So one of the reasons is that these micro LEDs would use materials that are 3-5 semiconductor materials, and they are already expensive and not abundant in nature. And then the idea of using tens of millions of LEDs, where each LED is a pixel, and then we are using green, blue, and red colors. So whatever the resolution is times 3 for using the 3 different colors, all that add up to doubling the price tag for the consumer.
Okay, so if I understand your answer correctly, there's one the high price tag due to the material, and second is due to the technology itself, because you have to make a very dense RGB pixels.
Correct.
Right.
Yeah.
So which one is the major factor that caused the price, the high price?
Between the two?
Yes.
I do not know.
Okay, then. So then let me change my question slightly. Then by using the technology or the approach you propose today, so can you, I understand you can reduce the cost of the material. Can you also reduce the cost of manufacturing or the technology pixels?
The cost of material. Yes, the cost of material, yes, because we would have silicon carbide as a carrier transport layer instead of the 3-5s and other substrate materials that would be used. In terms of manufacturing, I think we are too early to comment on the manufacturing, because we would have to figure out a design for manufacturability, and then we would probably be able to comment on that. But material-wise, yes.
Okay, very good. So let me ask the audience again. So any other questions and comments? Okay, so since I don't hear any further comments and questions, so I'm not going to take this opportunity to thank the speaker again for excellent talk today. And also I would like to thank the audience for attending this seminar. And I'll see you next week then. Bye-bye.
Thank you very much, everyone. Thank you, Dr. Zhu. Thank you, Dr. Kitai.
Bye-bye.
Thank you, everyone.
Bye-bye.
Bye-bye.
Bye-bye.